Again here, if you look at this calculation, do you see any problems with the calculation? Yeah, I think they screwed up the sig figs. Do you see that? How many decimal places should we have? 2, because of this. There's a fewest number of decimal places. Let's just make sure. So this is many, this is 4, so we should have 4 sig figs here. But let's take a look at this calculation. Do you see this calculation? Is that right? No, this is wrong too. This should give us, but it's 2 decimal places, so it's the same. We won't change anything. This one, is that right? 1 sig fig? Actually, it is right. We're only allowed 1 sig fig here. We could carry extras to avoid round off. They round every single number. If you round every single number, you're going to have more round off error. But how come we only have 1 sig fig here, but 4 sig figs here after we get rid of that extra decimal place? The reason is the rules are different. Addition and subtraction versus multiplication, division. And so that's with sulfur. So 4 different isotopes. Just that was the other. And so up to this point, what we talked about is the composition of atoms. You know, protons, neutrons, and electrons. You know, how many of each? We can figure out. We talked about the structure of atoms. What's the structure of atoms? Nuclear atom model or the plum pudding model, say. Nuclear atom model. And so if we know the composition and structure, then we should be able to figure out the properties. We want to know the properties. And so we want to know the properties based on composition and structure. However, how are you going to use that information? So if something has 10 protons, what are its properties? If something has 13 protons, what are its properties? Well, one thing we can do is, 10 is element neon, 13 is aluminum. And so we know the properties there. And so what we're going to do first is we're going to correlate, because I don't know how to predict. Can you predict? If something has 51 protons, can you predict its properties? No. And so we have to do a little bit of kind of memorization here. The memorization that we have to do is we have to correlate some properties with composition and structure. And so while somebody else has already done that for you by the periodic table. The periodic table, Mendeleev and Meyer, these guys, what they did was they arranged elements in terms of properties. And if we look at a column in the periodic table, a column is what we call a family of elements that share similar chemical properties. And if we look at a row is called a period, and in a period, the chemical properties gradually change across the period. And so an example is this. All the metals are grouped on the left here, and the non-metals are grouped on the right here. So as we go across a period, we gradually change from metallic, what we call metallic properties, to non-metallic properties. And so over here, we start off with cesium and end up with radon. And so this is it. And so what we need to do is we need to correlate this so that we can make predictions, because do we want to have to memorize? How were all the properties for these determined? By observation. Some of these properties were predicted by patterns. One property that was predicted by pattern is they discovered silicon, Mendeleev, and tin, but they figured that there's got to be something in between silicon and tin, so they predicted there's an element that is yet discovered, has yet undiscovered, and that fits in between silicon and tin, and it's correct. Germanium was found later on. And so there are some patterns that they predicted, but yeah, that's patterns in the overall picture. The thing is, how can we make a prediction based on the pattern? So if something has, let's say, 4 protons and 4 neutrons, tell me its properties. Can you? No. And so what we're looking for is we're looking for a pattern. Once we have a pattern, maybe we could have a law, the law of properties, chemical properties. If we have law of chemical properties, then we can predict it. But we don't. And so the first thing we're going to do is we're just going to look at the general organization of this. And then we're going to try to make predictions based on it. And so, and when we have the general organization, we can make predictions based on the position. But can you make, if we didn't have this here, can you make predictions based on the composition? So, as an example of that, fluorine is crazy reactive. And that's 9, element number 9. So if we go to element number 10, is that even more crazy reactive? No. So fluorine's crazy reactive, but neon is crazy stable. It's totally unreactive. And so why is it that we jump from 9 protons to 10 protons and all of a sudden it goes from crazy reactive to non-reactive? Neon's really stable. And so those are the questions we got to answer. So those are the things we're looking for in patterns. We're trying to find the patterns to come up with some kind of law to help us understand the properties. But looking at this, does anything come up? And so you could stare at this over and over and look at a simple correlation, a simple correlation being, why is it that going from, let's say, 1 proton to 2 protons makes a huge difference? And so we go from hydrogen, which is pretty reactive, to helium. Does helium explode? Have you ever tried to ignite a helium balloon? Will it explode? But a hydrogen balloon will. And so we go from 1 proton to 2 protons, it doesn't explode, and then 2 protons to 3 protons. Will lithium explode? Yeah, it's exploded. Computer batteries, laptop batteries, phones. How many of those have caught fire and exploded? And so can you have predicted that without knowing this? This is based on observation entirely, but we don't want to do everything based on observation, because if we do everything based on observation, then it's a lot of work. And then there's some patterns here. The patterns would be like silicon here, but then those patterns are somewhat limiting because we all have to have the overall structure of this down. And so a good proper theory, atomic theory should be able to explain things. And so does atomic theory up to this point really explain the differences between going from hydrogen to helium to lithium, 1, 2, and 3 protons? Does it really explain it? No. Do you see a pattern there? Not really. And so you know what? This atomic theory is not enough. We're at the end of chapter 5, but it's not enough. This is not a good theory, because a good theory should give you a good visual picture of what's happening. And we don't have a good visual picture of what's happening because you aren't really able to predict anything chemically. We can predict things chemically based on pattern and where they reside here, but we need something more. We need a deeper understanding. So that's going to come in later. That's going to come in Atomic Theory Part 2. Atomic Theory Part 2 talks about the theory of chemistry. The theory of chemistry is called quantum mechanics. So we're going to get to that later. But for right now, this is where we end the chapter. We end the chapter just learning about some of the properties that are observed. And so on the left we have the metals, on the right we have the non-metals, and how things transition over. There's a transition zone. This transition zone is between the metals and the non-metals. This transition zone is called the metalloids, or the semi-metals here. So metals on the left, non-metals on the right, and the metalloids, or semi-metals, at the border. Then we divide it into main group. Main group are the first 2 families or columns, and the last 6. This big block in the center is not part of the main group. This big block in the center is called the transition metals. And these ones sticking outside here are the lanthanides and actinides, which are the rare earths. Then we have certain families, like the noble gas family, etc. So we talked about this, the numbers on the periodic table. Talked about the periods. The periods are the rows. The families are the columns. We have the main group, the first 2 columns and the last 6. Then we have the transition metals. This is not so. We're gonna learn this as we go along. It's not so critical. Transition metals or elements, metals, nonmetals, metalloids. We'll talk about these as we go along in the properties. And so we just classify sulfur as a nonmetal based on its position. These are the elements that Carpellicci says to memorize. I want you to memorize more, though. I want you to memorize the ones on the sheet. Ones on the sheet, you know, like calcium and scandium is missing, titanium, vanadium are missing, and then silicon, actually aluminum, and then what is it? Gallium, semiconductor, germanium, etc. Arsenic. You have to memorize a little more than that. All right, that's chapter 5. There's not that much time. What I'm going to do is I'm going to talk about chapter 5 homework. Let's take a look and see what it looks like here. Let's see if I'm still logged on here. Yes. A little bigger window than this. Okay, what homework problems did I assign from chapter 5? Does somebody have that? This?
1, 3, 5, 7.
Okay, 1, 3, 5, 7. All right, let's take a look at 1. According to Dalton's atomic theory, can more than one compound be made from atoms of the same 2 elements? Yes. Yeah, more than one compound. Give me an example. CO2 and CO, H2O and H2O2. Yeah. That's the law of multiple proportions. 3, show that Dalton's atomic theory explains the law of definite composition. How would that show? What is the law of definite composition? I know this was a while back ago, but water consists of 2 hydrogens and 1 oxygen. If matter were infinitely divisible, then we should be able to change the proportions. Maybe just a little bit less hydrogen, a little bit more oxygen, or whatnot. Or salt, salt is what? Do you know the formula for salt? NaCl, 1 sodium, 1 chlorine. Can you just decrease the proportion of sodium just a little bit in the salt? No. That's the law of definite composition. And it makes sense if we have atoms, but if we have matter that's infinitely divisible, then it doesn't quite make sense. The answers are here as well. Yes, see figure 5F too. The law of definite composition. Okay, 1, 3, 5. What's next?
5, 7, 9, 11.
Okay, thanks. So the all the odds then. The chemical name for limestone, a compound of calcium carbon and oxygen, is calcium carbonate. Have you memorized the elements yet? And how many weeks has it been? 4 weeks? What you're going to find is, and I did a survey, only 1 or 2 people have memorized the elements so far, but we're going to have a whole bunch more memorization starting with the next chapter. And so you don't want to overload on the memorization stuff, so if you can. You're not going to have as much time to memorize this new stuff, unfortunately. But one of these is like carbonate. What is carbonate? You're going to have to memorize that. Just straight memorization. When heated, limestone decomposes into solid calcium oxide and gaseous carbon dioxide. From the names of the products, tell where you might find the atoms of each element after the reaction. How does Dalton's atomic theory explain this? And so, what happens to the calcium in calcium carbonate? It ends up in calcium oxide. Here. What happens to the carbon? The carbon ends up in carbon dioxide. And what happens to the oxygen? The oxygen ends up in both calcium oxide and carbon dioxide. So it ends up in both. Eventually, we'd like to write equations for this type of stuff. Once we learn more, we'll call nomenclature, but the nomenclature requires additional memorization. So the calcium atoms and some of the oxygen atoms are in calcium oxide. The carbon atoms and some of the oxygen atoms are in carbon dioxide. Okay, that's 5. Let's go to 7. Sulfur and fluorine form at least 2 compounds. SF-fluor, this we call sulfur tetrafluoride, tetra being 4. And this is called sulfur hexafluoride. Sulfur tetrafluoride, hexa. Did you guys memorize those? Can you repeat them for me? Oh yeah, math. That's a different numbering system than this. Math app pro. That's good. But so explain how these compounds can be used as an example of the law of multiple proportions. So how do you explain that?
The compounds that atoms come together in whole number ratios.
Yeah, whole number ratios here. Number ratios. Sometimes they say simple whole number ratios. Let's see what the answer says. So they're saying a ratio of simple whole numbers, 4 to 6. 1 to 4, 1 to 6. Let's go on here to 9. Advances in technology and science often progress hand in hand. What advance in technology was necessary to set the stage for the discovery of the electron? Did I assign this? Yeah. Mistake. I don't know. I mean, maybe the vacuum chamber. Well, actually, this is the basis. The CRT is the basis for the mass spectrometer. The CRT, what led to the advances for CRT? 1, glass blowing, glass making, 2, in order to blow glass, you need a high temperature furnace, so maybe furnace, energy. There's an interesting documentary, especially about the calcium carbonate. They were talking about Roman architecture versus the other architecture in the world, and they said it was because science and technology that the Romans could build such fantastic concrete structures, the aqueducts, Colosseum, whatever else. And it's because they were able to produce concrete. That's why. And in order to produce the concrete, they had to have 2 things. 1, they had to have time to do experiments, and 2, they had to have high energy sources like coal to generate the high temperatures that are required to decompose limestone. And so the decomposition of limestone in the previous problem was there was a reason for it, and they said it was because they have plentiful food. If they have plentiful food, then they can spend their time doing science experiments, and that's how they developed such advanced architecture for the time. I know we're almost out of time, but let's see what they say. This was a mistake. I wouldn't have assigned this because there are too many to list, you know. And so here, the invention of the Crookes tube, a high-quality vacuum tube, you can cancel that. Yeah, the Crookes tube. This is a vacuum tube. Well, is that such a huge advance? You see that guy who used a soda bottle? Is that such a big advance in technology? Use a soda bottle, drill it, and then put some silicone seal around it, and then get a pump that he salvaged from an old refrigerator to create a vacuum. You could try using a vacuum from your house, you know, to generate a vacuum. People do that, you know, to compress things. Our vacuum is like your house vacuum. It's so weak. And so you needed a decent vacuum. And so I would think of the invention of a decent vacuum, because you need a pretty high vacuum for that. All right, let me just do one more since one more. So it's 11. And so 9, don't worry about 9. There are too many to list. The mass of an electron is about 1/2000th of the mass of the hydrogen atom. Express this fraction as a percentage. What percentage of the mass of the hydrogen atom is due to the remaining subatomic particles? Let me sign this one too. As a percentage, you know how to convert it into a percentage. To convert a fraction into a percentage, you just multiply by 100%. And so this is 18. Let me just do this really quick. 1837. To convert anything to a percentage, you multiply by 100%, and that converts it to a percentage. And so let's just see what their answer is. See, so they multiply by 100%, they get 0.0544%. And so this second part doesn't. The second part is, okay, if that's the percentage of the mass work, this second part doesn't make sense to me. The whole question doesn't make sense. And so I'm sorry. I just two problems. You know why? Shoot. Now I realize what happened. I did the homework based on the 6th edition because that's all I had at home. I left my 7th edition here. I looked at it, I thought the 6th edition and the 7th edition were the same, but it turns out they're different. So I need to, did anybody start this homework yet? No? I'm going to change it a little bit, but we'll do it together in class. These are the wrong problems. The homework is going to be based on the edition. Now the homework, if you have this, you have the 6th edition.
Because that's what it said on the thing.
Oh, no, I'm sorry. Yeah. What are we on? Are we on the 7th edition or the 6th edition?
Yeah, I need to know. struggle street over here. It was bad. It was real bad.
Do you guys know if on the syllabus it says 6th edition or 7th edition?
It says 6th edition.
The one that they sold in the library is the 6th edition.
The one they have in the library is 6th edition. What about in the bookstore?
Oh, yeah. It looks like
6th edition?
Yes.
Okay, then I use the 5th edition.
Okay.
Yeah, so these problems don't look familiar to me, that's why. And I wouldn't have signed this, the second part to this problem makes no sense for me because,
Okay.
so, yeah. But we'll do all the homework problems, the ones that I want.
Okay, so do them tonight or?
No,
or
we'll
you're
do it
gonna
in
post?
class tomorrow.
Oh,
the chapter 5.
The chapter 5 homework we're going to do in class since it's kind of tight between the end of chapter 5 and the test. We'll do the homework.
Is chapter 6 going to be on the exam?
No.
okay. Thank you.
Okay, so in case I don't ever say you guys by any chance, like stealing our spot? No, like I don't see you guys. Oh, like find you guys because I get, probably not gonna go further. I have questions on chapter 4.
Yes.
Yeah, 21, 23, and 31. And 43. Well, everything technically.
Okay, chapter 4. What section is 21?
That is section 4.3.
Okay. Find the pressure of the gas in mercury in the mercury manometer shown if the atmospheric pressure is 747.4. The figure didn't load.
It's right here.
What did you get? Can you draw? You need to draw like the seesaw type balance.
Yeah, well, what I did was, well, I just couldn't do it. Actually, I just didn't know exactly what to do. So what I ended up doing is just looking at the answer and see how they did it. And yeah, and then they eventually just went to scientific notation. But you say that any answer that we have doesn't need to be in scientific notation.
Mm-hmm.
All right. And
So how did you set this up? The manometer. This one.
Well, me, I didn't get to know what to do exactly, but
Which one weighs more, the gas or the atmosphere? You see the gas is on the inside, the right side. What's pushing down on the mercury on the left side?
the gas inside.
No. outside here is the atmosphere, the weight of the atmosphere, 30,000 feet of air or whatever.
So it's the air?
Yeah. It's the air pushing down. So which one weighs more, the air outside or the gas inside?
The air outside?
The air outside? How come? Which one's pushing down with more force? Inside or outside?
Inside, because it's like...
Yeah, if this were a seesaw, the seesaw's tilted like this. If they're pushing down the same, if they weigh the same, so which one weighs more? The right side must weigh more because the mercury is being pushed down farther than the left side. You see that? So, basically it's this. You can set the level equal. So on the right, it weighs this much. On the left, it weighs this plus the height of that. The height of that liquid, mercury, is 173 millimeters. So you have 173 millimeters pushing down here, and how many millimeters of air pushing out here? It's a given in the problem.
It would be 747 torr.
Yeah, which is how many millimeters?
$173?
No, a torr is the same thing as a millimeter of mercury.
So then it would be 747 millimeters of mercury.
Right.
And then I just add those two up, and then I get the pressure, which is converted back into torque. Okay. For number 23 also, just the last bit, it says what absolute temperature corresponds to the temperature the student meant to record. So me, I just understood it almost like, what would it convert to? So, I don't know if that's what they're really asking for.
Well, actually, did you finish this one?
Yeah.
Well, what did you get?
I ended up getting 920 torque.
920 torr. All right. And then, I'm sorry, which was the next one? You doing?
Number 23, this one.
Okay. And what's your answer?
I ended up getting, for Fahrenheit, negative 492, and for Celsius, negative 291.1.
Okay. And then what's next? They're asking more than just that. What else are they asking?
They asked, what would you guess the student was trying to record? Me, I'm thinking that he maybe wanted to record in Celsius. And the nature of things at that temperature is that it would be freezing. The molecules would be just vibrating.
They'd be vibrating?
Well, like very little.
How little?
Like you wouldn't be able to
Okay,
see.
well, define absolute zero for me. What is absolute zero? You look in the book for that if you want.
Isn't it when nothing is moving? When everything is just like completely frozen?
Yes. Nothing's moving.
Okay.
And then, if nothing's moving, what's the temperature?
Absolute zero.
Yeah. Absolute zero. Can you go below absolute zero? like minus 18 Kelvin. Like nothing's moving at 0 Kelvin, and so minus 18, nothing's moving even less. That's minus 18. Oh,
Like you could go below 0, right?
yeah, how can you go below 0 Kelvin? 0 Kelvin means nothing moves. Hey, somebody asked you for some money to borrow, but you're broke. But you can say, I'll give you minus $18.
That's not what it makes sense.
Hey, then they might go, that's ridiculous because there's no such thing as minus $18, right? Well, then you go, okay, I'll give you minus $8. Is there such thing as minus $8? And you go, why? Well, because, once you have no money, you have no money. And then once you have no motion, you have no more motion. Can you have negative motion?
No.
Like, yeah, there's no such thing as negative motion. And so basically it's this. You can only go to stop moving. You can't go less than stop moving, because once you stop moving, you're broke. You have no more movement. You're not moving. How can you go lower than that? You can't. So high temperature, it's moving fast, and then it gets colder and colder, producing there's no more motion, and then you stop moving. You're broke. You have no more energy to move. If you have no more energy, how can you lose more energy? Do you have energy to give?
You can't gain anything.
There's nothing you can do. So the point of that question is there's no such thing as minus 8 Kelvin. The students screwed it up, or minus whatever they wrote. What do they write? Minus 8 Kelvin?
18.
Minus 18 Kelvin. There's no such thing as minus 18 Kelvin. It just doesn't exist. They must have meant something else.
Next one is number 31.
Okay.
It says a variable volume container holds 24.3 liters of gas at 55 degrees Celsius.